small. That's represented by this graph on this slide, where we're plotting the cumulative percent of faults detected against the number of triggering variables. Okay, we'll explain a little more about what we mean by the variables. But what's interesting here, obviously, is the asymptotic nature of 6 different studies or 6 different sources of errors found in software across a diverse set of industries: medical, a NASA database, server, a browser, network security, and traffic collision avoidance. Next slide, please. Okay, we've all had code that we've subjected to tests, and what I have here is examples of what we mean by two-way variable value interaction-driven failures. Okay, so for a piece of code, suppose you're inputting 3 different input test values. The test values are 3 different variables, and you can either have success or you'll have a failure. Now, in the matrix there, we have the variables identified as pressure, volume, and velocity. 3 possible of many scenarios are captured here. Suppose you put in a pressure value of less than 10 and it causes a failure, independent of what you put in with regard to volume or velocity. That would be an example of what we call a one-way interaction. But if instead of that you input the pressure less than 10 and a volume greater than 300, and that triggered a failure, then that would be an example of a two-way interaction. And then obviously at the bottom, if you had to put in all 3 variables to trigger a failure, that would be a 3-way interaction. Well, NIST has come up with a combinational coverage tool that measures the capacity of a test suite for detecting faults due to these kinds of interactions. Now, this isn't code coverage measurement that's based on statement or branch. It's just talking only about the effects of the input variables. Next slide. Okay, here are the mechanics of using the NIST tool. Okay, say you're an IV&V analyst and you were looking at test cases and you identified 3 test variables that the developer had used, and you had determined that all 3 were binary type variables, and there were 5 test cases that the developer had used. And so V1 can be either enable or disable, and V2 can either be side A or side B source of avionics, perhaps, and variable 3 could be either an average or minimum of some kind of internal set of information. Okay, well, what you would do if you have that kind of information, you can save it in Excel in a .csv file format. And if you're unfamiliar with that, I was too before we got started on this, but yes, it's in your Excel as an option. And so you see in the small box at the lower left, the representation in this file format of what the values are for the 3 test variables. Okay, that serves as your input to the test, the NIST test tool. And what it does is represented by on the right side of the chart here. And I'll go ahead and say it, that you can do this manually. Obviously, I've done it here on this chart, and you can circle in red what the interpretation of how these 3 variables and 5 test cases are represented. But the NIST tool does this all for you. So you see there's 12 two-way combinations, and this test set has covered 11 of them. And for 3-way, there are 8 combinations, and we have 5 test cases represented there. Next slide, please. Okay, the NIST output a chart that we see on this slide, and the top part of it is the dashboard, if you please, of how you operate the test. But what I want to introduce to you here is the coverage being represented by plotting the percentage coverage of the test versus the percentage of each of the T-way combinations. And in this example, first of all, this is easy to remember, the upper right-hand corner, anything that's beyond the red line represents no coverage at all of this test suite. And then anything under the red line represents what the two-way coverage is for this test suite. And as you remember, there was only one combination not represented. And so it does cover a goodly portion of the graph. And then everything under the blue line represents the three-way coverage, which is 60% across the board. The tool, one of the things we suggested to Rick and Raghu is modifying the tool to identify missing test cases so that you wouldn't have to take this information and try to go back to your IV&V analysis and just determine it from the data that you have there. So it gives you this image. It takes a little bit to get used to, and later when Rick talks, he's going to show you a variety of examples of this, and he'll interpret them for us. Next chart. Okay, I'll go ahead and jump to the conclusion. What we did was we looked at, as I said, a heater control system that had been performed, that had IV&V performed on it. And the conclusions that came out of this is that the NIST tool does provide a structure for recording and reporting test coverage. And that is very supportive of the idea of having evidence for your assertions on the quality of the software. And we found 4 different applications that would be possible, and they're kind of they're laid out here kind of in a prioritized sense. This tool can be used as an inline IV&V analysis tool, both by the analysts and by the peer reviewers. And an example is that it would analyze the coverage or lack of coverage of a developer's test. Okay. Our judgment that you ought to expect a moderate overhead for a worthwhile value added. Now, let's interpret a little bit. All analysts have their spreadsheet that they use to interpret what the developer has done and what we essentially think of the quality of the work done there. So let me just suppose that in that spreadsheet you added a few columns that would capture the test case variables as you're going through your test case analysis. Capture them and then have them saved in a CSV format and run the tool periodically as you go through. And perhaps maybe as you go through some section of a domain that you're responsible for, you could break it out in several subsections and then run the tool periodically for each of those. Okay, so that's one application. Again, you'd expect a moderate amount of overhead. You have to add some work in order to do this, but it does give you a record that you would not have had before. Okay, number 2 is as an inline verification tool in our JSTAR IPS, for example, in the lab. A lot of software is developed there. A lot of software is tested there, both from in-house development and outside development. And in both cases, there are a set of tests that are defined for the software, whatever its source, to determine how it works. We all know this. Okay. So in this case, you have the advantage of using the NIST tool as you identify the test, as you define the test, before they are run. And to me, that, again, it gives you some structure for recording what you're planning to do, and it will show you what the coverage is. I think this would be a low overhead for a high value added in the test planning. I think it could simplify, or it would certainly give you another layer of assurance and something that you could point out as you in your report of what you've done. Now, 3 is really the scenario that we used in coming this far in this subject. We did essentially an IV&V audit of what Adel had done a year ago for a very small part of what he does. And so if there's a need for auditing anything that we've done, this NIST tool could be effective again in capturing the coverage. Now, we weren't able to just use the existing spreadsheet that Adel used during his analysis. He instead had to generate a separate spreadsheet of the events, and so there was some overhead to do that. And I say we only looked at a small piece of what he did. So overall, if you audited an entire IV&V analysis, it'd be significant overhead for the value added. But if you had a need for it, it could provide again structure for what has been done. And then finally, as a macroscopic IV&V tool, perhaps you want to compare all the testing in a given project, or even all the testing across multi-projects in the form of their test plans. And there will be work extracting that information. But if you needed that kind of high-level insight, then the tool would be applicable there. Next slide. So our recommendation, first of all, we say the value of this tool must be proven in IV&V field trials. And so the recommendation associated with that is, number one, let's put the NIST tool and its instructions for use into the catalogs of methods. It's a candidate. It hasn't been proven yet, but we think it's a good thing to do. And let's try it out in real application. So, as I said on the previous chart, using the tool during an active IV&V project, including the peer reviews, for evaluating the test coverage of the developer's test plan, and also during analysis of the developer's test case script as well. You can also implement the tool in the lab, JSTAR IPC, as a verification test planning aid to measure the coverage of tests as they are planned and before they are run. And applications there would be in-house development, during in-house testing of the developer's flight software, which we have, during in-house development of test tools and other support software, which we have, and during the development of simulators, which we have. And then fourthly, consider use of the tool in comparing developers' test plans among projects. That might be a meta informational activity that would be of value. And we also recommend we consider collaboration with the Air Force and Johns Hopkins APL, as they have used the tool, and it would be good to compare notes with them. And then at some time in the future, when we get fully versed in how to use the tool and what its value is, introduce the tool to software developers for their use as well. Okay, next slide, and I'm going to hand it over to Rick.
Okay, thanks, Charlie. Just wanted to point out before I get started that NIST is basically the U.S. National Metrology Institute. We are right down the road, about 3.5, 4 hours from here, so come and see us. So I'm going to talk about application of the concepts that Charlie introduced to an example NASA project. And this was a small project, but it illustrates a variety of different things that, that we can see with this, this approach. I also want to point out that the tool was started at NIST, but it was capabilities greatly expanded by a researcher from SINAM, which is the National Metrology Institute in Mexico. So we were thankful for that. Itzel Dominguez Mendoza did that work. So let's move on. Okay, next please. Okay, all right. This is just illustrating the thermal system that we were looking at. So a couple of different types of sensors, thermistors or PRTs, and then we have the batteries which we need to maintain the temperature for. So seems like a simple problem, but can be very complex. There are a lot of different sensors involved, 34 different sensors, 16 of one, 18 of the other type. And so we're going to talk about examples of how we look at combinations of those things as well. These operate under the control of a set of flags, and the flags are intended to designate which side, for example, to look at, and so on. So we're going to look at examples of that next. So 14 different tests, and as we can see, there are flags here that are involved in controlling the software, the battery heater control to enable or disable, the side for the heater, and telemetry as well. And the control flag says average or minimum. That looks at whether we're going to average the sensor temperatures or consider minimums of the temperature sensors. And as we pointed out before, 16 of one, 13 thermistors, and 18 of the others. So first, we looked at the coverage of flag combinations. So let's talk about what this means with respect to the tests involved. So there were 14 different tests, and the tests had different settings for the flags. So as Charlie mentioned earlier, the upper right-hand corner represents the area that was not tested. Those are two-way combinations. If you look at the upper right-hand corner outlined by red, the red is the line for two-way combinations. So that represents a few combinations that were not tested. So that's something that you might want to look at, either do additional tests or look at maybe why tests are not needed and so on. The blue line represents three-way combinations, and the green line represents four-way combinations. Now there's a little bit more information on this chart as well. If you look at the red line, which extends from X of about 0.66 all the way up to 1, what that tells us is that roughly 2/3 of the combinations were covered with all settings. So when you think of taking binary variables two at a time, you've got 4 possible settings, 0, 0, 0, 1, etc. So this says that 2/3 of the possible combinations of these flag settings were covered with all 4 of those possible settings. And if you look at the horizontal aspect of the red line, that is at 0.75. So that says that 1/3 of these combinations were covered to the 75% level. In other words, only 3 of the 4 possible pairwise settings of those binary variables were covered. So it's a little bit more information. You can get that. Same thing applies to the blue line and the green line. So you can see that, of course, the coverage drops off significantly for four-way combinations represented by the green line. Now we looked at sensors, and here the coverage is not quite as high. On the other hand, this is also an example of a case where you may not want to apply this kind of analysis as much as before. The flag settings, obviously looking at combinations of flags, that can have a very significant impact on the operation of the software. But if we're looking at combinations of sensors, which are very redundant, 16 of one, 18 of the other, so they're basically reporting the same kind of information. Interactions among the sensors, and that of course is what we're looking at, are interactions. So interactions among duplicated sensors may not be as significant as interactions among flags, which of course are very significant. Here's another thing we looked at, the minimum and average settings. So in this case, even though we only had, out of the 14 tests, we had 4 tests with the minimum flag set, 10 with the average flag set. The coverage is very similar for these. And the coverage is okay. It's not extremely large. As you can see, in both cases, the horizontal red line is at 0.5, so that's telling us that about 50% of the possible two-way pairwise combinations of values were covered in most cases. A little bit more, you get up to 75% for a small fraction of some of these. And again, 3- and 4-way combinations were not covered as well. Now, one thing to point out is that this was only looking at 14 tests. There were many other tests that were applied for this particular effort because the developers applied a lot of tests. So this is not saying that the system was only tested with these 14. This is just the 14 that we looked at. But this is a way to give a quantitative measurement of the coverage of the input in those tests. here's looking at the side A and side B sensors. So this is kind of different because it shows how one is covered significantly more than the other. So if you look at side A, we have pretty good coverage of that. Again, the upper right-hand corner represents the area that is not covered. So those are combinations that were not included in test, so there may be more risk there. If you look at the two, you'll see that A is covered better than B because that upper right-hand corner region is much larger for B. So that's more risk for B, essentially. And next. This is just to show the raw data. This is the kind of thing we look at. This is only a few variables, of course, and in a lot of realistic testing situations, you're going to have many more variables. We have one user right now who is applying this approach to a system with 358 variables, many thousands of tests. So that would, of course, be very difficult to analyze manually. And again, what we're looking at are combinations of these values. So we're looking at two-way combinations, three-way combinations, and so on. So trying to do that manually would be very difficult. Next. Okay, don't have to read the details of this. We have full documentation, but I just wanted to point this out to illustrate what the tool looks like and step through some of the features of it. So the upper part is just how you load it and enter your tests. Illustrates what the tests look like. If you notice in the upper right-hand corner, there is a little block that says parallel. So this has the ability to invoke multi-cores, because right now you might have 4 cores on your laptop. Next year you'll have 8. Pretty soon you'll have 256 and so on. So this is a real nice feature. And Adel that I mentioned earlier added this. We specify what level of T-way combinations. So that's looking again at 2-way, 3-way, 4-way, 5-way, up to 6-way combinations of variables. The reason for that, the reason that we stopped at 6, of course, is, as Charlie mentioned, empirical data says that at least among the several thousand failure reports we've looked at, 6-way combinations or 6-way interactions among variables or less were involved in everything that we saw. So we've never seen a failure involving more than 6 variables. So again, if we cover all 6-way combinations, we've got very good testing. Doesn't mean we test, doesn't mean we have perfect testing, but we have very good testing. And then at the lower right-hand corner, that shows the results that are output by the tool. And next. Okay, last slide, more or less on time here. This is interesting now. This is something I had not mentioned previously. Two particular features to look at here. So far, we've talked about binary variables, but we know that most testing involves much more than that. So one thing we can do is we can use the tool to define equivalence classes, because a lot of variables you're going to have involve ranges of values, which can be very large. So just like in all testing, there's nothing different here. In all testing, you have to select representative values, somehow abstract that large range of values into something smaller. So this allows you to define those classes within the tool. And then at the bottom lower left-hand corner, this is critically important. This is constraints. Now, in any testing situation, you have certain variable settings, certain combinations of variables that are just not possible. You just don't see them. There's no reason to test them. And if you have a test that contains that combination, then the test is going to be useless because you'll never see that in practice. So an example there, of course, is if we have an application that's designed to run on a variety of platforms, we don't want to see a test that says Internet Explorer running on Linux, because we don't see that in the field. So any test that contains that particular combination is not going to help us, and it may help it would cause us to lose combinations that are also contained in the test. So we can define very complex constraints that reflect real-world systems using this approach. Basically, it lets you specify first-order predicates, the kind of thing that you would see in any formal spec or within a program. So that's a very nice feature. And then the lower right-hand corner illustrates just a small example showing the coverage for 2-way up to 6-way combinations. So we can do very complex and interesting things with this tool. So in summary, what do we get out of this? It gives us a quantitative measure, an actual measure, not just a metric. There are metrics such as code complexity, lines of code, and so on that are correlated with problems, but not directly. This gives us a direct measure of the proportion of the input space that was not covered. And that's also questions.
Any questions in the room? We will take questions on the phone if anybody has them.
Once again, if you would like to ask a question, please press *1 and record your name.
Any questions on the phone?
It's from Mary.
Okay, thank you.
Yeah, hi, this is Mary. I think this question is geared more towards the first part of the presentation. They had mentioned the IV&V audit tool and the significant overhead, of course, of auditing everything. I'm just a little unfamiliar. What is your auditory approach? I mean, in our field, we do have internal audits. How are you kind of handling that at IV&V? And how do you know when you're kind of capturing it at the right level?
Okay, this is Charley, Mary.
Hi, Charlie. Yeah.
Yeah, I don't know personally about even if we have an audit tool. I just postulated that as a possible application, and given that that was the nature of what we had to do in order to evaluate this tool, I said, yes, it could be done if indeed you wanted to do an audit. I'll have to.
Yeah, an auditory, and I think that's a very good idea, actually, when I thought I said, wow, that would be good in an auditory, capacity. And then I said, the next question is, I'm like, well, how are they handling their audits over there?
I don't know.
Okay, no problem. I'm sure as I go through the grapevine and talk to people, I'll find out. But thank you, Charlie. Appreciate it.
Any more?
We have no further questions from the phone.
Thank you, Marla.
Okay.
All right, we're going to go ahead. Thank you, everybody. And we're going to go ahead into the next presentation here in just a second.